Hi everybody. So now we're going to talk about some concepts related to waves. If you're ever going to use an instrument that uses waves, for example, like a transducer. So the main idea for this one is that I mentioned it before, but when a wave moves, actually what moves is not, well, let's look at this for example. So this part of the slinky here, it vibrates up and down, but it doesn't go anywhere. It doesn't go sideways. It doesn't travel from left to right. It stays where it is. So what actually moves through a wave then is going to be energy. So waves are going to transmit energy. So the matter or the particles stay where they are, but it's energy that actually travels from left to right. And so because of that, we're going to talk about the rate at which waves send energy. And that's something called intensity. Pretty much either loudness for sound or brightness. It depends on what you're looking at. So for sound, this just means how loud it is, or how much pressure it impacts on your ears. And for light, which is going to be another kind of a wave, it just means how bright the light is. So we're going to describe how intense or how bright or how loud a source is by saying that how much energy gets transmitted to your ear per second. So if this is your ear here, your ear is going to detect the sound. And we're going to say your ear is going to have a certain opening, a certain area where sound can pass through. There's going to be an opening, about like this in your ear, where sound can pass through. So we'll say that each second, so as time goes by here, each second, how much energy is going into your ears and making your ears vibrate. So this we're going to define to be intensity. So intensity is pretty much the energy that's transmitted to your ear. That passes through your ear each second. Well, that not just your ear, but the area that like this opening of your ear here. So it's the area, it's the energy that passes through the area of your ear each second. And remember from a few chapters ago, energy divided by time, or work divided by time, is the same thing as power. So the actual way that you write intensity is it's going to be power divided by area. It's just how much power gets spread out over a given area. So this part I'll just leave as is. So there's some units for intensity, depending on whatever instruments you use, but the main one is going to be in decibels. So loudness or brightness can be measured in decibels, or dB. So you can see here some examples. Just a low noise has about 10 decibels, and to the point where it gets painful to hear sound, you can get up to about 150 decibels. And here again, this is another chart that shows you the range in terms of decibels. So yes, the loudness can be measured in a couple of different units. It can be measured in terms of pressure or pascals, or in decibels, dB. So let's look at an application of that, which is going to be for transducers. So then this is going to combine a few of the things that we talked about, mainly the Doppler effect. The way that you're able to create an image is that, as for example, you have a baby. So the sound comes in, and the baby moves around. And remember, the Doppler effect has to do with a couple of things. It has to do with sound waves moving, and if the source is moving back and forth, then that's going to change the frequency, And then you can detect that change. And just from that, you can actually create an image of what's happening. So then the transducers use the Doppler effect to create an image. So there's some other concepts that we're going to use when we learn about how the transducers operate. And first thing is just the basic idea, which is called wave interference. So this shows you here that if you have two waves and they're moving towards each other, so when they actually meet, so when one wave arrives on the top of the other, what you're going to find is that they're going to add to each other. And then so the wave is going to be twice as high when they're on top of each other. But then they're not going to, eventually they're going to pass right through each other. So then later on, one wave is going to be on the other end, and both waves are going to be on opposite sides of each other. So this is what you see here. So this is before they meet. When they meet, they're on top of each other, and they double in height. And then let's say that this is wave 1 here, this is wave 2. And after they meet, wave 2 is over here, wave 1 is over there. So they pass through each other. So we can use this to make things louder. So you can see here with the speaker, if you set the two speakers correctly at the right distances, when the waves arrive at the same point here, at this point here, they're going to have the same orientation. So the top of one wave will meet the top of another wave, and they'll add up to get an even bigger wave. So this is called constructive interference. So let's look at an application of this. This simulation is going to show us how two waves can interact with each other. So the first wave is going to be this blue wave here, and the second wave is going to be this orange wave. And notice for both of them, they're both upwards. So this one has a height of +3, and the orange one also has a height of +3. So let's go ahead. We're going to keep our eyes focused on this point at the center here, where they're going to meet, and we're going to count how high this wave is. And let's have it run a little slowly. So as the two waves approach each other, the central point here, you notice it starts to rise, and it rises to a height of 6. So let's try to do that again, and I'll pause where it rises. So these two waves are coming towards each other, and they're gonna, when the two waves meet, they rise right there. You see the height of this new wave, or the combination of these two waves, is 6. And the reason why is because the two waves, they have the same orientation, so they add to each other. So whenever two waves have the same orientation and they add to each other, that's called constructive interference, where each wave had a height of 3, so 1, 2, 3, but adding both of those waves together gives you a new wave with a height of 6. So this is called constructive interference. And let's just run that one faster now. So whenever two waves meet and they interact with each other at the point where their heights add up, that's called when their heights add up, that's called constructive interference, and that occurs at this location here. So now let's actually try the other case. Let's have this thing run slowly again, and let's change the orientation of this one. So let's see what happens when these two waves meet at at the same location in the center here. So just keep your eye on where my cursor is. If you notice, the height isn't going to change at all. It stays where it is as those two waves pass by each other. So it goes nowhere. And the reason why is because the waves are canceling each other at that location. So whenever two waves interact with each other and they have opposite orientations and they cancel, that's called destructive interference, which is what's happening here. So if you notice, that central line didn't move at all as those two waves passed by, because they're canceling each other because they have opposite orientations. So let's try it again here. So as the two waves meet each other, they have opposite orientations, they cancel. So this height stays 0, they cancel out there. And that's called destructive interference. So again, the height stays 0, doesn't move as the waves pass by because they cancel here. So here, if you have two waves, but now they have opposite orientations, so that one is up and one is down, when they actually meet, they're going to cancel. And then after that, they'll proceed, after they pass through each other, then they'll proceed as they were before. So this is wave 1 here, this is wave 2. When they meet, they cancel each other out, and then wave 2 passes, it goes to the left, and wave 1 proceeds to the right.